In this video, we're going to look at the trend with electronegativity. It's the ability to attract or steal electrons from a neighboring atom. Hopefully this trend kind of sinks in with you, because electronegativity is a topic that comes up all throughout the year. It really affects the properties of a particular atom. Going down a group, electronegativity decreases. So think about it. Going down a group, the atoms get bigger. One of the main reasons is because we have lots of energy levels. 1, 2, 3, 4, 5. He's a big atom. So we said this attractive force is weak. Weak attraction. Because just naturally the electron is far from the positive nucleus, but then there's also the shielding effect, where the inner orbitals and inner electrons block the attraction between the nucleus and the outermost electron. Okay, so now let's add a neighboring atom. Here's his little nucleus. He's a moderately sized atom. There's his electron. If this attraction is weak to start with, the likelihood of this big atom attracting another electron is probably pretty slim. The attractive force is just not strong enough. So going down a group, the big atoms, they're like gentle giants. They're not going to steal your electrons. There's just not enough attraction. The atoms you have to worry about are the little guys. Going across a period, we said the attraction increases between the nucleus and the electrons. Well, yeah, as you add more protons, the nucleus becomes more positive, so there's a stronger attractive force between the nucleus and the electrons in their own atom, as well as electrons in neighboring atoms. So picture this small atom. Couple energy levels. Here's his electron. We said this is strong. A strong attraction. Strong enough to remove electrons from another atom. So here's my second atom, my victim. 1, 2, 3. We'll make him moderate again. Here's his electron. When that attractive force is strong, we can steal this electron. Rips it right off. This is a yes. The small atoms with high attractive forces are more likely to remove electrons from neighboring atoms. On a periodic table, we said francium was the largest atom. Francium, down in the bottom, had the largest radius, so he actually has the lowest electronegativity. A gentle giant. He's not going to steal your electrons. In fact, francium has enough trouble holding on to his own electrons. We said his ionization energy is very low. Now, normally then we were saying helium was the smallest atom. Helium had the smallest radius. It had a really high ionization energy, lots of attraction. However, do you kind of notice that it's blank on this little graph, this little periodic table? The winner of the award for having the highest electronegativity is actually fluorine. Fluorine has the highest. Highest electronegativity. Because if you think about it, we're talking about attracting or gaining electrons. Why would the noble gases really want to gain electrons? They have full orbitals to start with. Now, some of the noble gases do have electronegativity values, but these are usually big atoms that have d orbitals. So they do have kind of like a dumping ground for extra electrons. But some of these smaller ones like helium, neon, argon, they're not going to steal electrons. They don't need electrons. They already have very full stable orbitals. But then fluorine is a very small atom, lots of attraction, and think about his electron structure. His last orbital would be the 2p with 5 electrons. To fill that orbital, he only needs one more electron. So in other words, fluorine really wants another electron. On this graph, the trends follow suit for the most part. Going down a group, ionization energy decreases. So I can look at electronegativity decreases. Here's a group going down, lithium, sodium, potassium, rubidium, cesium. There's a gradual decrease in electronegativity. And then as I grow across, look what happens from like lithium to fluorine. Electronegativity increases big time. Fluorine has the highest rating. On a scale of 0 to 4.0, fluorine gets the 4.0. Electronegativity increases big time going across for all of these groups because there's so much more attraction between the nucleus and the outermost electrons that we can even attract neighboring electrons. Okay, so kind of related is something called electron affinity energy. This is the energy that's released when a neutral atom gains an electron. If you want to think of it as an equation, now we have a neutral atom, we can just call it atom X. If he gains an electron, he'll form a negative ion because we're not adding protons, so if we have an extra negative electron, we'll have a negatively charged particle, we call it an ion. When this happens, energy is released. So we release energy, it's a product. We're usually forming a more stable atom. So again, think about like fluorine. Fluorine already had 5 electrons in the 2p. He really wants to fill the orbital with 6. Full orbitals are stable, and when something is stable, energy is released. So again, going down a group, electron affinity energy decreases because these guys have low electronegativity values. If you have a low electronegativity, that means you're not likely to gain electrons in the first place, so then you're not going to release a lot of energy. But going across, as we see an increase in electronegativity, these are the atoms that are more likely to steal electrons, and when they do, they'll be more stable and they'll release energy. I always remember this term, electron affinity energy. If you have an affinity for something, it means you really like something, you really want it. Well, these atoms over in this region of the periodic table, these are some of the highest electronegativities. These guys usually have 5 electrons, 4 electrons in their p orbitals. They're really close to having full orbitals. If they could just gain 1 or 2 more electrons, they'll fill the p orbitals and become very stable. They have an affinity for electrons. I have an affinity for chocolate. I really like chocolate. These atoms have an affinity for electrons. They really want them. So when they do gain the electron, they'll release energy.